Alrighty, good evening, folks. How's everyone doing? Yes. Alright, let's wrangle it in. We got a lot of stuff to get through tonight. So, I just want to point out, folks, sort of a summary, just as a reminder how this goes. If we've got class the next day, you've got pre-work due that night. The only time that doesn't hold is when we get an exam. Because I don't make you do pre-works the day of an exam, because I want you studying for that. So, for example, let's see here. Tomorrow's the 31st, a Wednesday, and because on Thursday we have class, there are your two pre-works, right? I try to always put little QR codes in there, but sometimes, I shouldn't say that. For this class, I've only just started putting in QR codes. If you're ever missing the QR code for that, you should just be able to access the hyperlinked videos if the QR codes aren't there. The other thing is that this is sort of my outline for when things are due. This is the course. This will be sticking as close to this as I can, unless you see something. Unless I make an announcement, at least for the pre-works, this is what you have due. Sometimes we'll be a little bit off with the in-class works, but we'll try to just trudge forward with those pre-works. The other thing is, if you look at the homework sets. I went ahead and finished updating all the due dates for the homework sets through the rest of the semester. So those are all up and good to go for you. Okay? Those are all due on Sunday nights. I tried to, where you have kind of a hodgepodge, I tried to color code them so you can kind of see that, those clusters, to help you see that a little bit better. So those are your due dates for the homework sets. Please, folks, some of you have asked, if you want to get started on one and it still says still updating, if you get started on it and you hand in the one that you printed off to work, you're fine. Okay? If I've updated something and you don't do that, one problem that I've updated, that was on me for not getting up earlier, but you're fine. So just if you need to get started on things early, you have the ability to do everything for this course early, except for the exams. Okay? So you've got that for you. What else? Speaking of, you can see they're listed elsewhere, such as in the syllabus, but you can see the exam dates on here. We have 3 exams in here. Notice there's not a lot of time between exam 2 and exam 3. That's just how it goes. You're going to be learning brand new methods in those 2 weeks, and I want to test you on them right away before we go into the advanced topics for those. Okay. All right, you should have a handout that says Gaussian elimination. Part 2. Part 1 was done as pre-work, and I want to go through this with you here. So let me stay out of your way. Okay. I've given you the steps to the row reduction algorithm. I don't find reading those steps all that particularly helpful. It's more something that you work enough of these that you've sort of memorized that algorithm. That's really what you want to do with it, instead of pulling out a set of steps. The one thing that I'll point out about those steps is that they're very programmable. You can ask a computer to do the exact same thing that you do in those steps, which is, there's some great computer algorithms for doing the row reduction algorithm. It's not the best thing if your matrix is, say, 1,000 rows by 1,000 columns. There are far more efficient ways to do row reduction, or to solve matrices, but it is a rudimentary, surefire way of always getting at the solution. Okay. So I want to summarize a couple of the results that we've seen. Let's suppose I've got a system, we'll call it star, a system of linear equations with n variables. Okay. When we go to solve a system, we have 3 different possibilities. Okay. We could get we could have the situation where a solution exists and it's unique. We could have the situation where the solutions exist and they are not unique. And we can have the situation where solutions do not exist. Okay, those are the three possibilities here. Okay? Let's give some terminology to this. When a solution exists, we say that that solution is consistent. So a consistent system is one that has a solution. Now careful. If a solution is consistent, it might have one solution, a unique solution, or it might have infinitely many. Okay? And then I think we can do this. Let's take a shot at this. Math doesn't always work the way you expect it to, but what do we think here, folks? If a solution does not exist, we say the system is inconsistent. Great. Okay. By far, in my opinion, the most complex case to consider is when you have consistent systems with infinitely many solutions. I feel like when you get an exact solution, you guys should be feeling okay, especially after doing the homework on that. You should be feeling okay with what we mean by that. Okay? And also, how do you recognize a scenario where you have an inconsistent system? What jumps out through the row reduction algorithm?
You can't do it? No, wait.
What do you mean you can't do it?
You have three variables?
Not necessarily. So I don't want to limit ourselves to the case where we only have 3 variables or 10 variables or 1,000 variables. What are we looking for when a system ends up being inconsistent? Josiah? When the row results to a false equation. So by that I mean you might have something like, it might look like, you might have a row that looks like this. Somewhere in there. This would correspond to the equation 0x plus 0y plus 0z is equal to 3. Do you see why that would just be the statement 0 equals 3, which is false. That's when we have an inconsistent system. So I think actually after a little bit of time, those inconsistent systems will stick out like sore thumbs. You let us spot them. Okay? The hardest case, in my opinion, is when you have a solution, but you actually have infinitely many. And that's what you guys got some practice with in your homeworks for this, and I want to talk about just a little bit more. Okay?
Was there a reason that he used x sub 1 and x sub 2? Like
Mm-hmm.
x? No.
So sometimes when we just have a 2x2 system, we could use x and y for our variables. If we have a 3x3 system, we might use x, y, and z. 4x4, I guess we could use x, y, z, and w. But what if we had a 27x27 matrix? You've already run out of letters in the alphabet, right? And so we start using subscripts for the variables, and that's a common thing to do in this class. We'll just jump back and forth. If you want to use x, y, and z, where I'm using x1, x2, x3, that's your choice. Yeah, but there will be times where you'll find it convenient to have those subscripts, and other times where it really doesn't matter. Yeah, great question. Okay, so here we go, folks. If we have n variables, and after performing the row reduction algorithm, we have n pivot columns, then we say that the system either has a unique solution or no solution. Okay, now the idea is if I end up with something like this, 1, 0, 0, A, 0, 1, 0, B, 0, 0, 1, C, then the unique solution to this is the ordered triplet A, B, C. That's the unique solution to it. And so what we're doing is each time we run through that row reduction algorithm, we're giving a consistent or an equivalent system of equations. We start with one system of equations, we manipulate it to a different system of equations, and then this is about the simplest of all systems of equations, right? Like you would have loved this on an Algebra 2 test that says solve the system x equals a, y equals b, z equals c, because the solution was just presented to you. Okay. Now, I do say that it could be no solution, but the only way that would be no solution is if, let's see here, how would that happen? In pivot columns and variables, there is a way it could happen, and that would be if I gave you one extra equation that ended up being inconsistent. So the way that would happen is if I gave you something like 1 that reduced down to this, A, 0, 1, 0, B, 0, 0, 1, C, and then I have a third row that looks like this. If that were the case, then we have no solution to that. But that's not kind of the fault of how that row reduced. It has to do with this last row right there that would have given us no solution. So that's that no solution case. I'm not going to try to draw an arrow to it. That's too messy. Okay. Did everyone see that? Okay. So the one thing I didn't say here is, although I said I had in variables, I didn't tell you how many equations I had. And so it is possible if I started with 4 equations, 3 unknowns, for one of those to result in a false statement. So I have to take into account that case. Okay. A system has no solution if any row corresponds to an inconsistent equation, such as the one that I mentioned right here. So that's the same thing that I've mentioned up above there. That's the same thing as the false statement, 0 equals 1. Okay. Okay, so maybe you've noticed this, maybe you didn't in doing the homework. If when you put the equation in REF or RREF, folks, generally I'll be happy with going down to REF, but there will be times where we put it in the entire reduced row echelon form. Just as a reminder, the reduced row echelon form requires there to be zeros above any pivot ones as well as below. And so it often requires a little more work to get there. Does that make sense, folks? Do we want to talk about that? Okay. So if the matrix is consistent but has fewer than n pivot columns where I have n variables, then the solution will have n minus p free variables where p is the number of pivot columns. This actually gets to the heart of one of the big ideas of linear algebra. Let's look at this system right here. This is a system of how many variables, folks? 1, 2, 3, 4, 5. Yes, 5 variables. I gave you how many equations? 3 equations, 5 variables. Okay. How many pivot columns did we get?
3.
1, 2, 3. So we have 5 variables with 3 pivots. What I'm saying up here is we will have how many free variables in this? And you should have started to discover this doing your homework. We would have 2 free variables.
And those would be constants always? Like those would always be...
We represent them as not as constants but as choices, like let x2 be s or let x3 be r, and I like to use the letters s, r, and t, or r, s, and t for those free variables, but that's a personal choice. But you want to pick, it's a parameter, and you don't want to use the same letter for the different parameters. So let's go ahead and give the solution to this first as an n tuple. Okay, so let's go ahead and work through this. So by the way, folks, I've already moved on beyond the row reduction algorithm, saying, I think you've gotten that algorithm down. Okay? If you don't have that algorithm down, no worries, but you need to get it down ASAP. Okay? I'd be happy to help you with it during office hours, or I'd be happy to folks in the Math Center might be able to help you. There's all sorts of resources. By the way, I've had this happen a few times where students have said, hey, not in this class, but hey, do you have any recommendations for how to do the row reduction algorithm? And I'll say, yes, you did a pre-work on it. And I'm not being facetious. You saw it in the pre-work, and not everything clicked the first time you saw it. But a good thing to do would be what? Go back through the pre-work a second time and see if it clicks better. Now, if you've gone through the pre-work twice and things aren't making sense, no worries. Like there's something, that means I didn't do a good job in the pre-work. And come talk to me and I'll try to come up with a better explanation. But I have some students that seem kind of like, it's like they're afraid to revisit those pre-work videos, which is, the whole reason why I made them videos rather than a one-off lecture is that you get to revisit them as often as you want. So, I have already done the row reduction algorithm here. That's tedious, and it would be kind of mean to give you a 6x3 system that was just filled with non-zero numbers. That would be a long time to row reduce, right? Potentially. Okay? So I've already done some of this. Now I will find ways to test you on your ability to row reduce, but hopefully without making you spend an hour on it on an exam, because that's not very useful for any of us. Does that make sense? Okay? So you'll get plenty of practice on row reduction, and if you're not feeling comfortable with it, you want to come see me. Yeah, Xavier.
What if we had only ones in like the x sub 1 slot? Like the rest were all zeros in a sense. Like there's only those 3 in a line going down.
Like in the x1, x2, x3?
No, x1, just all in x1, there were ones.
So that would have corresponded to me giving you 3 equations that were just multiples of one another, and you can't solve that. So you'd have infinitely many solutions, but the best you can do is say, let's pick a parameter for each of the, you'd have everything except for your first variable would be a free variable. Yeah, and so like it's kind of just, your solution would just be all the points that lie along that first equation, which might live on a hyperplane or a plane or something. Yeah, great question. Okay, so let's go ahead and give the solution of the system as an order 5 tuple. The first thing to notice is that we have how many pivot columns here? We've got these 3, so I've got 2 pivot columns. They're going to correspond to x2 and x4. Okay? So let's see here, let me just say that. We see that x2 is free. I'll let x2 equal And then I like to use, I'm going to end up with how many of these free variables? 2. So I like to use S and T. If I'm going to have 3, I like to use R and S and T, but that's just a personal choice. It's your letter choice for that. So I'll let x2 equal S. And then x4 is free. Let me get out of your way. x4 is free. So I'll let x4 equal T. Be careful, folks. I try my best. My S's do tend to look a little like 5s. Let me know if you ever have any questions on that. Okay. So now that I've done that, notice that we could say that the third row gives us this equation. Let me see here. Third row gives us this equation right here. That x5, or in fact 1x5, is equal to 7, or just x5 is equal to 7. Going forward, I won't worry about dealing with those ones, if that's okay. So that's x5 is 7. Okay. So, folks, this goes back to something you learned a long time ago in algebra. Way back in algebra, if I gave you the equation of if I give you two equations with two unknowns, two linear equations with two unknowns, we could think of the graphs of those as being two separate lines, L1 and L2. And so solving a system of equations meant finding where those two linear objects intersected one another, right? Now, harder to visualize, but I had you copy down a diagram in your homework, was what do linear objects look like in 3 dimensions? They look like planes, right? And so asking you to solve a system of 3 equations, 3 unknowns, was asking the question, where do these 3 planes intersect? Now, it just naturally extends upwards even though we can't look at it. So, I don't know what a 4D hyperplane is, a 4-dimensional hyperplane is, but it's just 1 dimension more than we had before. It's a linear type object that lives in R4. Now we can't visualize it, but that's okay. We're still asking the question. We've got several of these 4-dimensional linear objects, and we're asking where do they intersect. Okay. So this is a 5-dimensional hyperplane. We can't visualize it, but the same way we ask the question where do these 2 lines intersect, I'm asking you the question where do these 3 hyper 5 planes intersect. That's what I'm asking. And we just found that the last coordinate of that has to be 7, of that ordered 5 tuple. Now so you always start at the bottom row after you've run the row reduction algorithm, and you just sort of, I call it laddering your way back up. So if I jump back up to the second row, here, this is the equation x3 minus 4t is equal to 5. Does everyone see that? Double check that. Make sure that makes sense. Okay, instead of writing 1x3, I just wrote x3. And then I've already replaced x4 with t. Yeah?
Can you remind me how we decided that the x2 and x4 were the 3?
Yeah, great question. So this matrix in REF or RREF form has how many pivots? 3 of them. Where are they? For the x1 variable, the x3 variable, and the x5 variable. So the remaining 2 columns correspond to non-pivot variables, and those will be my free variables. Yeah, great question. Great. All right, so the second row gives me this equation, so I get that x3 is equal to 5 minus 4t. And then if I go back up to the first row, and this can sometimes involve, oh, great catch there, thank you, let me put that in blue, plus 4t, thank you. And if I go back into the first row, this could sometimes involve a lot of cleaning things up. In this case, I would get that x1 minus 6x2 plus 3x4 is equal to 0. Now, folks, there is no one...
Plus 6.
Oh, thank you, thank you. Thank you, thank you. Plus x4, and in fact, I could go ahead and also replace those now with s's and t's if I wanted to, or you can wait until the next step to replace them. That doesn't matter. Okay. Thank you, folks. So, I want to point out that there is no one example I can give you that's good enough to learn this topic, right? It takes about 4 or 5 different examples before you start encountering all the different types of scenarios you would see. We'll just keep working through them, but that's why I've had you do a bunch already in the homework for this. So, for example, notice that there was no constant in this equation here, but there very well could have been in this case. So there's sort of all sorts of different cases we can encounter. If I were to solve this for x1, then I get x1 is equal to, let's see if we can do it right this time, minus 6s minus 3t. Did I get that right? All right.
Are you recording?
I am recording, yes. I should be. Let's double check. Yep. Okay. So now I can go ahead and give the ordered 5-tuple the solution to this equation. So here it is, folks. It's minus 6s minus 3t, comma. x2 was the free variable s. x3 was 5 plus 4t. x4 was the free variable t. And my final value was the constant 7. How are we doing with finding those 5 tuples? Okay. All right. So now I'm going to represent this what I call vector form. Okay. What I don't want you to do is just give me a single column vector. Okay. So if you do this, you're not wrong, but that's not how I want you representing the solution. So you could write this way. And you're writing it as a vector that's already been added together. What I'm after is that you break it up in terms of the scalar parameters that you have. So instead, what I'm actually saying, so this is not what I want. It's not false, but it's not what we want here. So what I'm after is this statement here, 0, 0, 5, 0, 7 for the constant vector, plus a vector that depends just on the parameter s, scalar multiple s, minus 6, 1, 0, 0, 0, plus the parameter t, negative 3, 0, 4, 1, 0. How'd we do with representing this in vector form, folks? Now, how do we interpret this? Well, one way to think about this is that for sure we've got infinitely many solutions. Okay? For sure we've got infinitely many solutions, and what you're allowed to do is pick any real number you want for s, any real number you want for t, plug those in, add this together, and you get a solution to this equation. So we do have infinitely many solutions, but it depended upon how many parameters. 2 of them. Okay? Now, one way to think about this, if you've had some vector calculus before, if you've worked with vectors, is that our solution can be thought of as this vector plus a scalar multiple of this vector plus a scalar multiple of this vector. That's another way to talk about it. Now, if you've had Calc 3 and you've described surfaces before, what type of surface is this? Now, although we're talking about R5 and we have these 5 tuples in R5, which are hard to even imagine, this is just an equation of a plane. This is the equation of a plane living in R5. Okay? So just like in R2, 2 equations could intersect at a point. Or what else could 2 equations do in R2? They could have no solution because they're parallel and they never intersect each other. Or there's a third possibility. It turns out that the 2 lines that I've given you are just 2 lines stacked atop one another, and the solution is a line living in R2. So that's what we have here. In this case, I mean, I can't even draw this picture, but my solution is a plane. Why? Because this is two-dimensional that lives in R5. Okay. Bringing it back even a little bit easier, if we had just had one independent variable here, and that's all I was talking about, then that really looks like the vector form, the vector equation of a line, if you've had Calc 3. If you haven't had Calc 3, no worries. I'm just trying to draw some ties. You don't have to recognize that for what we're talking about here, but it does make some nice connections. Okay? So if I have infinitely many solutions with one parameter, that means my solution is a line living in whatever space I started in. If I have two parameters, that means my solution is a plane living in whatever space I started with, as far as asking where did all these equations intersect one another. All right, that's deep enough for tonight. Okay, lots of hypotheticals could be asked there. If you do have questions about writing this in vector form, though, or writing this as an in-tuple, I'll take those. If you do want to talk more about these spaces and what do these solutions look like in these spaces, come on by during office hours. I'd love to sit down. It really just requires a good one-on-one conversation. I've had that with a number of you. But kind of with linear algebra, I give you problems, and I wait for you to come to me with your questions, like some sort of Yoda kind of thing. Like, you come to me with your questions when you're ready to ask. Yeah?
So no intervals needed to be stated because we already said there's two variables?
Correct. I mean, it might be, I think probably some people would argue, Charles, you ought to write S and T are any real number here. In this class, that's always implied, but some people might argue you ought to say that. I don't think I'll be a stickler for that until next semester, because I haven't been doing that. Or until next time I teach this, because I haven't been thinking of that. Yeah. Great. Okay. So folks, actually, these were the ones that were in your homework, so we'll just hit one or two of them. Okay. Okay. So let's see what we got here, folks. First of all, I've got a system with how many unknowns? How many variables? 5 of them. So I can't use X, Y, and Z, right, Xavier? And then I just start running out of nice letters to use, right? So we would think of this as the column corresponding to the variable x1, x2, up to x5, right? So folks, could you, from this matrix, rebuild the original system of equations? Well, maybe not rebuild the original system of equations, but you could rebuild a system of equations. How about that? Okay, you could. So what I want you to be able to do is be able to jump back and forth between talking about a system of equations and its corresponding augmented matrix. Okay? So in this case, we're with 5 variables here. We have how many pivots? 2 pivots, which means we have the remaining 3 variables are my free variables. So we have infinitely many solutions with 3 arbitrary parameters or 3 arbitrary variables here. Okay? I think I'm going to hold off on writing solutions on these because well, let's do that with one more here. We have 3 here. Fine. So let's see here. In this case, we have which variables would be free here, folks? X2, X4, and X5. So I'll let X2 equal R, X4 equal S, X5 equal T. Folks, you don't have to do that, but I like them to come out in alphabetical order, so that's just why I kind of worked that a little backwards. Okay, R, S, and T. I think that's alphabetical. Okay. So then we could go ahead and start representing our, I'm going to go ahead and give it in vector form. So our x1, x2, x3, x4, x5 would be, let's see here, the only one we get a number for is the first one, 3, 0, 0, 0, 0. I don't know if I can do this. Plus R, which would be -1, 0, 0, 0, 0. Usually, folks, I actually write out these equations, so let's just see if we can do it, though. S would be, so we have no, see, that's that variable here. So we'd have a -2, a -3, a 0, a 1, and a 0. I feel like I've got something wrong there, folks. Let me see here.
I think your R may have a 1 under the negative 1.
Yeah, I'm going to have to, I was trying to jump to this. We're going to have to just, I'm sorry, folks, I can't do this in my head right now. So let's just, well, you don't have to erase anything. I just want to start over on it. So the equation here, the second equation corresponds to x3 equals negative 3x4, which is s. And the first equation tells me that x1 is equal to 3 minus 2x4, which is s, minus x2, which is r. I think those are the equations there. So we end up with x1, x2, x3, x4, x5 is equal to 3, 0, 0, 0, 0 plus r times negative 1, and that's for x2, so 1, 0, 0, 0 plus s, which would be negative 2, 0, negative 3, 1, 0, and then the last one, which is t, which is just 0, 0, 0, 0, 1. Oof. How'd we do, folks?
So is that format, the solution format, what's the name of that format?
I call that vector form.
Okay. And then the other format, which is just, what is that?
As an n tuple. So not an ordered pair, not an ordered triplet, but an ordered n tuple, whatever your dimension is. Did I have a mistake here, folks?
For t on the middle 0, is it supposed to be a negative 1? Maybe I'm looking at the wrong one.
T is for just x5, and I don't think a t showed up anywhere in these equations unless I have an error. Yes?
So x5 is a variable even though it's column with all zeros?
Correct. Correct.
Why is it x3?
So for x3 here, notice that x3 has a pivot 1. We've only got these 2 pivot 1s in this. So those are not my free variables. Those are the ones that can be written in terms of the arbitrary parameters in this case. Yeah. Great. We okay, folks? So let's see here. What about B? What's going on with B? We have no solution. In fact, we now have better vocabulary than you had for your homework. We'd say that the system is inconsistent. And if you want to, you can go back up and label A as what? Consistent. I'm not too big on that vocabulary, but you'll hear me use it occasionally. A lot of people, other people make a bigger deal about it. Okay. Ooh, let's look at C, folks. How many variables do we have in C? 5. How many pivot columns do we have in C? Okay. Another way we'll say is that this has full rank. Okay. Another way to say that is the number of variables equals n. In this case, the number of variables is what? 5. And the rank, which is going to be the number of pivot columns, is equal to 5. And so whenever the number of variables equals the rank, you've got full rank. Okay. So there's all this vocabulary for linear algebra, and we're just scratching the surface with it. Please, the things that I'm asking you to do in the homework, those are the things I'm asking you to understand for right now. We're just going to keep revisiting these ideas as we go along, and you're starting to get better and better grasp of linear algebra. For anyone curious, like for a more Another way to look through it is I've posted those 3 blue, 1 brown videos, which tackles these from another perspective. There's lots of ways to teach linear algebra, and the more exposure you can get to the many different ways of thinking about things, the better you'll understand it. So those are pretty helpful as well. So in this case, we get a unique solution. Does anyone have trouble coming up with the unique solution here? I mean, because it's not fully in RREF form, it's not in the reduced row echelon form, you can't just read off the solution. Does that make sense? Except for the very last, we know that x5 is going to be 2, but then everything else requires you to kind of ladder back up. Does that make sense? But notice you will be able to ladder all the way up without ever having to pick an arbitrary parameter, unlike the other examples that we did this for. Any questions on that? Does anyone want me to work this? Yeah? Okay, let's do it. Okay. So we're told that we can see here that that row 5 tells us that x5 is equal to 2. Row 4 tells us that x4 plus 5x5 is equal to 1. So x4 is equal to 1 minus 5 times 2, or negative 9 there, I hope. How are we doing? Okay. So then, in your groups, go ahead and figure out the remaining. I'll let you do it. Go ahead and figure out what row 3 is. Okay. How are we doing with these? Is this helping having this?
Yeah, that's helping me read a lot better.
Good, good.
It's just I gotta keep updating it.
So it's just that, yeah.
It's 2.
I think you got there by clicking on my webpage. It has those links to the notes. Yeah. Yeah. Folks, just so you know, I think I've mentioned this a couple times, but I know how it goes. I've been mentioning a whole lot of stuff. Just as a reminder, all the way up here, yeah, it says 2023. I need to update that. But always on the title, on the header of this website, you can access a link to my OneNotes page. It's a little bit clunky, and you gotta kind of navigate. It will never remember where you left off, but you can navigate to these notes. Okay. And you're at the mercy of the internet. Here we go. Here you can see we can. Does that make sense, folks? So you have access to these. If there's anything that you're having a hard time seeing, or if you'd rather listen and then copy them down later, whatever works for you. Christian.
If there's one unique solution, I just want to make sure I'm understanding this right. Like there's a number for each variable that we come up for when we put this in our depth. Does that correspond to like all 5 of those planes intersecting at a single point?
Correct. Hey folks, Christian asked a question here. If I have 2 equations, 2 unknowns, and the corresponding matrix reduces down to having 2 pivots, then that means that you have found the point of intersection. And if I have 3 equations, 3 unknowns, and it reduces down to 3 pivots, okay, that corresponds to the unique point where those 3 planes intersect one another. That should match one of the pictures that you drew on your homework, where 3 planes all intersected. Now, unfortunately, that's as far as pictures can help you, but in this case, what we just found is where these 5 hyperplanes, I'm just going to call them hyperplanes, I don't really have a sense of what they look like, but they're the 5-dimensional equivalent of a line, okay, or of a, I don't want to say a line, of a hyperplane, I mean, just the next linear object up. You're finding where these 5 hyperplanes all intersect, and you found that they all intersect at a common point, as opposed to sharing a line in common, as opposed to sharing a plane in common, or as opposed to sharing some other linear space in common. Okay? Now, what they won't all intersect to be is what? They won't all intersect to be all along a circle or anything like that. How come? Because we are studying what type of algebra here, folks. I mean, not how come, but That's the inside, right? We're doing linear algebra. Okay. What do we get for our R3 here, folks? I'll let you guys help me out. We found that x3 is equal to what? 2. And then if we do that for R2, row 2, we find that x2 is equal to 23, I'm hearing. And if we do row 1, we get -2, and so we get the solution -2, 23, 2, -9, 2. In this case, there's no real benefit to writing this as a vector, although you could, I guess. But there are no independent parameters here, so it's just a singleton point where all 5 of these equations intersected. How are we doing with that, interpreting that? Good. Good. By the way, folks, if you got those numbers by looking at my answer, and I'm taking the answer now, somebody at some point ought to check my work. So just make sure you're always checking these. I've been getting a lot of good questions like, hey, I think there's an error on question 7 of the homework or something like that. So keep sending them to me. I do these on my lunch break when I get interrupted by emails, phone calls, people stopping by my office. Like if I were sitting down taking my time, I'd say, oh yeah, these solutions there are no errors in them. But I'm just doing as many solutions as I can to as many problems as I can whenever I get a chance. So I apologize for any errors in there. But hopefully what you won't ever see is like a conceptual misunderstanding. Those are pretty rare to show up. It's usually I write 2 + 7 = 1, which makes no sense. So, all right. I think I'm done with this. Let's go ahead and have you guys. What I'd like you to do. Oh, there's the different ways planes could all intersect. That was the picture that I asked you to copy for your homework. Okay, the different ways all those planes could intersect. What I can't show you is all the different ways 4-dimensional hyperplanes could intersect. Okay? Because we can't draw them, and there's probably far more possibilities than there are in the, when I just drew up here just a second ago, I did the 2D case. How many possibilities were there in the 2D case? There were just 3, right? We either had a point where they intersected, they shared a line in common, or they never intersected at all. But then once we bumped up to planes, we had all these possibilities with planes. 1, 2, 3, 4, 5, 6, 7. Okay. How do we go? Let's see, we had 3 in 2D, 7 in 3D. Ooh, take the dimension maybe. Raise 2 to the power of the dimension, 2 to the 4th minus 1. Maybe 15 different pictures or 15 different possibilities for 4x4 systems. Just a lot, but anyway. Okay, so what I'd like you guys to do this problem. Okay, in your groups, I'd like you to work through this. So notice this is an old test question. This is not in RREF form, so you're gonna have to solve this system, but it won't be too much work.
Reduce that to 1.
Yeah.
You get 1, and then I subtract it from 2 from 1. So under that 1, so I subtract the -3. Did I series
Sir. Do you prefer Norman or Gustavo?
Yeah, no. Okay. I want to ask you, what thing a zero is full of zeros? What you can do?
Yeah, so the algorithm says to move that all the way down to the bottom.
All the way down to the bottom.
Yes, but then your analysis at the end of the day will just be the same, just like we had with this one. At some point, maybe that row of all zeros actually showed up somewhere before that, and I moved it all the way down. But then then we keep doing the RAF algorithm on what remains, and then we can still do the same line of questioning. We've got how many pivots? 1, 2 pivots for our 5 variables, or 3 variables. How's that work? Good, good, yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, 121, 122, 123, 124, 125, 126,
Boy, this one's a little too easy, isn't it? You don't even have to row reduce anything. You just do the division steps, huh? That's okay.
So, the number of pivots equals the number of planes that intersect? Or?
No, the dimension minus the number of pivots gives you the dimension of the solution space.
Wait, so then five. So the dimension it's the dimension of the space.
So the number of pivots, the number of variables.
So number of
So it's this equation on the previous page, right? On the previous page, you have an equation on the first page there, where I said the number of free variables is the number of variables minus the number of pivots. And then that number, however many free variables you have, that's the dimension of the solution space. And this is going to take time to get, folks. I'm not looking for mastery of these ideas that we're talking right now. What I'm looking for is just what I've asked you to do in the homework, which is to do the row reduction algorithm, to be able to represent your solutions as 5 tuples or n tuples and then as in vector form. And we will keep discussing this throughout the course of the semester. Okay? It just takes a while to see all this. So I'm happy if there's some questions that you have. We'll just keep working on answering them. S.
No, because these are this intersects. These are 2 planes intersecting, so I thought that those. What do you mean? So 2 variables means it's 2 dimensions. So yeah, 2 planes. So these are 2 dimensions. No.
Yes.
May you check
That
my
would be
Yeah, let's see. I'm gonna put it up here. Yeah.
a plane. No, that's just 1. So our solution would be our solution would be linear in a 5-dimensional space. You lost me there. I lost myself.
All the solutions are linear. It's all linear. But
So the number of free variables equals the dimensions of the solution space. We don't know what that means. We'll have to ask about that when we get to it.
Well, what's the dimension of a point?
0.
0 dimensional. So if you have 0 free variables, then your solution's a point.
So dimension of 2 variables is a line.
Nope. One dimensional object is a line.
2 variables is a plane. 3 dimensions is a box. 4 dimensions is unknown.
No, just 3 dimensions is not a box. 3 dimensions is a plane, and you have 3 dimensions when you have 2 free parameters. I'm sorry. A plane is 2-dimensional. Yeah, a plane is 2-dimensional. We don't have a 3-dimensional hyperplane. I don't know what that looks like.
Yeah, so that means our solution would be a point. Yeah, so the 2 variables would be.
So I would hold off on writing that down, Xavier, for another 3 weeks.
Oh,
Yeah.
that's, you know.
that's what I got. How'd we do, folks? Did I get it?
Yeah, I just use different.
Looks good.
The hardest part of the day is
Gustavo or Norman, how'd we do?
Yeah, yeah.
Good? Okay. Thanks. Folks, how are we doing with this? Okay. Folks, is this impossibly difficult? No. Is it something you have to practice? Yeah, it's just kind of not natural for you to write expressions this way, and so it takes some practice. I know everyone in here is completely capable of getting it. That doesn't mean you can get it without practice. All right. Let's just say, here's kind of just that conversation. The graph of a linear equation of 2 variables is a line. The graph of a linear equation of 3 variables is a plane. That's as far as we can imagine. So the graph of 4 variables is a 4-plane or a 4-dimensional hyperplane, and that's just sort of as far as you can go with visualizing these things. Okay? But basically, I think that R3 is kind of the right level of abstraction, and the way you can think about it is the equations that I give you correspond to planes, and I'm asking you, how do these what points are in common to all of these planes? So notice in this case, here we had a unique solution. And we just had a single point where those 3 planes all intersect. By the way, I sort of wish this picture was adjusted. There's nothing that says that had to intersect at right angles. So that's a little bit misleading. Does it not have to intersect at right angles like that? It gets kind of hard to draw these. Here you can see that we have infinitely many solutions. You see that all 3 of these planes, you can see that all 3 of these planes intersect along this line here. That line is all of the solutions. How do you describe a line with as a vector? If you've had Calc 3, you know that you describe a line as some r0 vector plus t times some direction vector. But do you see there you've got that independent, that singleton parameter, that t? That's that one parameter that we find when we found one free variable. Okay? If you haven't had Calc 3, this is going to be a little bit lost on you. That's okay. I'm going to focus on the things you need to know, but I'm just trying to make some connections for those that have had it. Okay? So here we again have infinitely many solutions. This would happen when I gave you 2 of the planes. Like that picture means that 2 of the planes were actually identical. I gave you 2 different ways of describing the same plane. Okay? We could also have, in one case, I might give you all 3 of the same plane. And so you have, what are your solutions? What points do these planes share in common? All the points on any one of those planes, if they're all the same plane. Okay? Then these are all the situations where you had no solution. Okay? Now careful, does no solution mean those planes never intersect? No, it means those planes don't all 3 intersect at common points. Okay? All right, we'll leave it at that. By the way, people have been solving, I don't remember where I found this. People have been solving systems equations since the Egyptian days, and they've had different kind of algorithms, techniques for doing so. And it's not coming up, here we go. If you want a fun article, I've hyperlinked. If you want a fun article, I've hyperlinked to a discussion of like the different ways they've been doing solving systems of equations and then actually row reduction for lots of years. So fun little article there that actually looks at some historical examples. So anyway, quite a ways. I don't remember. I don't know. It's been a while since I've read the article, so I'll let you take a look at it. Yeah, you think you have a bad when you make a mistake with the matrices, but if you were chiseling it into stone when you do your reduction, yeah. Good point. All right. That's a good place to take a break. I've got that it's 55, so we can start up at 7:06. That would be great. Yeah. Okay. Wow, we're we're not incredibly far behind. This is a new experience for me. So you guys did a pre-work just last night on exact ODEs. And so I want to we'll do one refresher question with that, and then we'll do a nice little extension. Okay? So we saw in our pre-work that if I give you what's called a multivariable function, if you haven't had Calc 3, don't worry about that. Oh, did I not give them to you? Sorry about that. If I give you this multivariable function and it's differentiable, okay, and then suppose we have an this is only for first order, a first order ODE written in differential form. Okay, folks, I'm trying to really highlight for you because a lot of our techniques say if you have an ODE in a particular form, this is the strategy that we use. We're short one? Is there an extra one sitting around, folks? Thanks, Aristotle. Would you mind passing that to Bridger? Thank you. Okay. So a lot of our techniques go like this. If I give you an equation, I might have taught you how to solve it, but you have to first rearrange it into a particular form. So in differential form, it would look like that's true. That's fine. Let's just leave it like that. No, let's put it with the psi. So psi sub x of xy dx plus psi sub y xy dy equals 0. Then my family of solutions to this is just psi of xy equals c. Okay, so what's going on here? What we're going to imagine is if we could think of our ODE as coming from this function right here. It's kind of like this function right here generates the ODE by first taking the partial derivative of that function with respect to x, multiplying by differential x, and then taking the partial derivative of this function with respect to y and multiplying by differential y. And if the sum of those two is 0, then first of all, the ODE is called an exact ODE, and its solution is just that psi function. Okay? Now, I mean, this is kind of cooked. If it came from this, that's the solution to it. For those of you that have Calc 3, this is the same thing as there's an analog here between talking about conservative vector fields and finding the potential function that generated that conservative vector field. We're doing the exact same work, and there's an analog to there's a Calc 3 equivalent to what we're doing here. But usually I'm not just going to say, hey, here's an ODE, it came from this function, what's the solution? And your answer would be, well, that's the solution, right? Usually you have to go find this psi sub xy, right? And what's the general rule about looking for finding something? Finding a needle in a haystack. Your favorite thing to know up front is what?
If there's a needle.
If there's a needle in it. Well, how do you check? You do this test to check to see if it's exact. And if it is exact, then you know that the process that I taught you how to do last night will enable you to find that generating function, and that will be your solution. And we'll review that. If that's not making sense, or if it didn't make sense in a pre-work class, we're going to practice that once here. Okay. Go ahead.
Is there a more like intuitive explanation of why, like, what exact actually means?
Yes. I'm going to answer that. That's what the question is there a more intuitive answer? What does it mean when we do that check? So usually the way it's going to work is this. I'm going to give you an m of xy dx plus an n of xy dy. You're gonna put the equation in this form. What's the check to see if it's exact? The check is to see, does m sub y equal n sub x? Please don't get bogged down by the choices of m and n. if this goes with differential x, then I take the partial derivative of this with respect to the other variable. And if this is the d sub y, then I'm going to take the partial derivative of this function with respect to the other variable. That's what we're checking here. Now, if you've had Calc 3, there was something called Clause's theorem. It told you that if you had equality of mixed partials, or sorry, it gave you the situation for which you would have equality of mixed partials. What we're saying here is, I'm wondering if this m came from some psi of x. Right? I'm wondering if this m right here came from some psi of x. Well, let's check by first taking the partial derivative of that with respect to y. Right? That's what we did with our m. And then we're saying, if this is an exact equation, n would have come from taking some psi, that's a horrible psi, of y, and then I'll take the partial derivative of that with respect to x. So what are we checking for? We're checking for equality of mixed partials, basically, and if that's the case, then we can go find that generating function. That's the best I can do for an explanation of this. Yeah. Unfortunately, folks, a lot of the explanations in this class are not going to be very satisfactory. I will, whenever I can, dive into them, but there will be some things that are just a little bit more formulaic. So there's a little bit of an insight as to the connection there, and it connects to some topics from Calc 3, but that's kind of as far as I want to go and probably as far as I can go. Yeah?
When will we go over like an application of this to the real world?
Yeah. Great question. So we will get some good applications with our autonomous ODEs next week. And also next week we will solve some specific linear ODEs that I think will have some nice examples with some mixing problems. So this is the hard part, right? Students always want to know, wait, why is this useful? And then they tell me, I hate working story problems. You know, so I'll be bringing in some story problems, some good applications of this next time, or next week. We'll start bringing in a few of these. For right now, we're just like you did calculus for a while before you did any applications of calculus. You first had to learn your derivative rules before we really started doing the fun problems. We're kind of doing the same thing right now. And to be honest, we're sort of getting as quickly as we can to the more advanced techniques to do the more interesting story problems. So I would say that the latter half of this class will have more story problems than the first half. Yeah. But we'll talk about this. So yeah, we'll talk about that when we get there. Yeah. Okay. All right. So and somebody asked here, and the answer boils down to the multivariable chain rule. So I've given, I don't remember what that links to, but I'll let you take a look at that, Brandon, to see kind of a little more explanation where this comes from. So in our pre-work, we gave a method for solving exact ODEs, which we'll review below. But please note that this method assumes you've already verified the ODE is exact. Meaning, if you don't verify the ODE is exact, then I'm not going to accept a solution if you give it to me, and there's a good chance you won't be able to find a solution using this technique. If it's not, and if it's not exact, you won't be able to. So you first must verify the ODE is exact. Okay. Then we said an ODE is exact if m sub y is equal to n sub x. That was our result from last time. So let's go ahead and jump into it. But I said here that being guaranteed to be able to find that psi is the same thing as verifying that we have equality of mixed partial derivatives. Okay, so let's jump into this problem here. This is like one that we saw in our pre-work. So I'll go ahead and put this into differential form. Let's see here. I'll write it as dy dx is equal to, and then I'm going to go ahead and collect the minus sign up top there. If you collect it in the denominator, it doesn't matter, but you just need to take it somewhere. So this gives me, so folks, I'm going to cross multiply, if you will, and then take everything over to one side. So I think what we'll do is we'll do our 6y squared minus x squared plus 3 dy, and then I'll add this over to give me 3x squared minus 2xy plus 2 dx is equal to 0. And so it kind of doesn't matter what I label as m and n, and I don't even have it in the xy order that I had before. What am I going to do? We're going to take the partial derivative with respect to x of the first term, 6y squared minus x squared plus 3. That's our n of xy. And if I do that, we end up with, if we take the partial derivative of that with respect to x, I get minus 2x. Then I'm going to take the partial derivative with respect to y of our second term, the m of xy. And if I do that with respect to y, I get also minus 2, of the whole expression. So there's our, come on, 3x squared minus 2xy plus 2. And the partial derivative of that. Remember how, folks, this is not for people that have had Calc 3 before. How many of you had not taken partial derivatives before this class? No worries. I think there's about a third of you. About a third of you haven't done this before? This class? No worries at all. Remember, the way we do it is we say we're going to treat, in this case, the variable that we're not taking the partial derivative as a constant. So I'm going to treat x as a constant here, and I'm differentiating with respect to y. So even though 3x squared has a variable in it, it's not the variable we're integrating with respect to, so that term would be 0. Same thing with the derivative of 2 being 0. If I take the derivative of minus 2xy with respect to the independent variable y, that will just be the same minus 2x. Anyone who hadn't had partial derivatives before, does anyone have questions on, or I guess does anyone have questions on that?
Why would taking the derivative with respect to y for 3x squared minus 2xy if it's multiplying with dx?
Oh, so that's our check. So that's a good, I think that I'd just like to, if you haven't had Calc 3 before, no worries, but let's just leave it at the superficial level of saying, I'm going to take the, if this is the way it's written, I'm going to take the, if I've got, this is what's in front of the dx, I'm going to take the partial derivative of it with respect to y.
Okay.
And if this is what's in front of the dy, I'm going to take the partial derivative of it with respect to x, and then check to see if they're equal. So it's, you are deliberately crossing them. The true answer of what you're checking for, that was that, it's something called equality of mixed partials. You're checking to see if you have that.
And the order doesn't matter in differential form.
Correct. So like I mean, technically to be a differential form, I should have written this, I should have interchanged those two, yeah. But all I did was say, here's the function in front of dy, I took the partial with respect to x. Here's the function in front of dx, I took the partial with respect to y. Yeah. Vitaly, did that answer your question?
It did.
Sort of. I mean, it doesn't tell you why it works, but it tells you what we're doing.
I got a little bit of it.
Good. Anyone else, especially if they haven't had partial derivatives before? All right. So, oh, what a mess. So we've just verified that this differential equation is what? Yeah. Okay, so now we know there's a needle in the haystack. Let's go find it. Okay. Our strategy is to integrate one of the component functions with respect to the differential next to it. So, for example, here, we could go ahead and, I'm going to go ahead and integrate the 6y squared minus x squared plus 3. I'm going to integrate it with respect to what? With respect to y. Now, integrating it with respect to y will start to find the original phi from which this came from. The problem, though, is what if there was a term that involved just x? We wouldn't be able to recover that when we integrate with respect to y, because that would have been treated as a constant, and we wouldn't be able to recover it. Okay? So if I integrate this with respect to y, this is going to give me 2y cubed minus x squared y plus 3y. I could have probably combined those terms. And then normally, what did you do when you were just integrating to find a function of one variable? You'd put plus a c there, right? But the problem is we've got two independent variables, or we could have more independent variables. So we won't be able to find the original expression. We will be off by some term, potentially by a term that maybe it just has a constant 3, but it could also have the expression, say, 3x squared or 3 sine x. So the constant is in terms of everything that we haven't integrated with respect to. Okay. So then this is almost our psi of xy. Now what I'm going to do is I'm going to take the partial derivative of this answer with respect to the other variable that I haven't done this with respect to. So I'll take the partial derivative of this. Oops. 2y cubed minus x squared y plus 3y plus c sub x. And I'll take the partial derivative on the other side with respect to y. And so when I do that, notice I get negative 2xy.
Other side of by y instead of x?
Oops, that should have been the same variable. Thank you there, Catherine. That should have been c partial with respect to x. And notice that the first term on the left-hand side vanishes, the third term vanishes, and I get c sub x of x needs to equal, and then on the right-hand side, I would have psi sub x of xy. And then this next part is a matching game. So let's first, did everyone partial derivative with respect to x of the first term, that vanishes. That gives me minus 2xy. Third term vanishes. This will be, it's a derivative, so I'll just write with the subscript x on it. And on the right-hand side, we got the psi sub x. Everyone okay with that? Folks, I really want, especially if you didn't get to the pre-work, this may not be making any sense. So my first thing would be watch clear. But if you did the pre-work, please, if you have questions on this, ask the questions. Yeah, Xavier.
At the end, could we go over kind of, you had like an arrow kind of sheet that summarizes? We could just go over that.
Yeah, sure. Yeah, we'll do that. So, but what is our psi sub x? Psi sub x? If I go read the psi sub x, that would be the function that's supposed to be the function that's in front of x right here, right? So that would be 3x squared minus 2xy plus 2. It's supposed to equal 3x squared plus minus 2xy. And so now what we're going to do is we're going to make a positioning argument. And I don't know why. I find that in differential equations we make a positioning argument a lot. It's kind of fun, actually. So right here, everyone see that this right here is my minus 2xy on both sides. And so by position, then our c sub x of x has to equal 3x squared plus 2. So the constant function that depended just on x or maybe other constants, when we took its partial derivative, it's supposed to come out to be this. So all I have to do now is integrate c sub x.
Ugh.
see here, come up here. So all I have to do is integrate my c sub x of x dx, which is the same thing as integrating, I'm not going to be able to fit it on here, oh well. Integrating my 3x squared plus 2 dx. So on the right-hand side, I'll just get whatever that constant term was supposed to be, and here I get x cubed plus 2x, and then I get plus c, but that's just the regular plus c that you have in integration. That's just, we're only off by a constant now. Okay. So in our very first step of trying to figure out what our psi sub xy was, we were almost there. We integrated one of our component functions, and we were almost there. We were only off by a term that just depended upon x. Okay. So then we took the partial derivative of both sides again, and then we made this positioning argument, and we said, okay, that term that could only depend on x, its partial derivative with respect to x should have been 3x squared plus 2. So then we integrate both sides of that, and now we figured out what that c sub x was supposed to be. So now I'm ready to say that my psi sub xy that I've been trying to find will be what I already thought it was, which is that 2y cubed minus x squared y plus 3y plus this additional component that I just found right here, which will be my x cubed plus 2x plus c, where that last c truly is just a constant and not some constant function, not depending on one of those variables. So then how do we represent our answer? We represent our answer to the original ODE is just this equation right here, 2y cubed minus x squared y plus 3y plus x cubed plus 2x is equal to c. And that's how we give our solution to that. Okay. Folks, if you're finding this difficult, we'll just try it a few more times. I think by the end of the homework set that has this on it, you'll have it down. But please, if you're struggling with this, especially if you've not done this in a Calc 3 class, come by and see me. I'd be happy to help you. Okay? In my opinion, there's just sort of a diagram that reminds me of what I'm doing as I'm trying to find my psi sub xy. So I think of it like this. I start out with my n. Let's see. In this case, we started with our n sub xy, and I integrated to find psi of xy plus c sub x. Okay. So here I integrated to find this. Let me put this in a different color, and I'll move it elsewhere so it's easier to see. So the diagram that I think goes with this is we started with our n of xy. That was the function in front of the dy, and we integrated to get our answer psi of xy, but we were off by some constant function in terms of x. Okay? And so then we took the partial with respect to x to get psi sub x of xy plus c sub x of x. And then we integrate one more time, and I should say this was integrate with respect to y. And this time we integrate with respect to what the second time? X. And that gave me my psi of xy, now just plus a constant. Okay. To be honest, if you've had, in Calc 3, you have to do it one more time. You'd have to differentiate with respect to z and then integrate with respect to z, and that actually kind of reinforces the whole procedure a little bit better. Yeah?
And we can go the other path.
Oh, yes. So I chose to start with n and integrate with respect to y. I could have just as easily started with m, or the other component function that was multiplied to the differential x, and done the exact same thing and arrived at the exact same place. Yep. It just matters that you do it with respect to all independent variables by the end of the day. Yeah. Great. Okay. So, I'd like everyone to try to mimic that step that we just did. Go ahead and try it here in number 6. Give it a shot, this procedure. What's that, Caleb?
Ahead of the game, I see how that is. Or did I do that?
No, you're right.
Okay. I had a feeling there wasn't enough for me to solve the whole thing. I mean, I can predict, but
How many of you went looking for a needle in a haystack without confirming there's a needle there? Did you start trying to integrate? Oh, good. What's the first thing we need to do here? If I put this into differential form here, I'd have 3xy plus y squared differential x plus x squared plus xy differential y is equal to 0. So this is what I'd be calling my m. This is what I'd be calling my n. And again, the choice of letters doesn't matter there, right? The thing is I'm going to take the partial derivative of this component function with respect to the other variable, and when I do so, I get 3x plus 2y. And when I look at my n sub x, when I take the partial derivative of the second component function with respect to the variable x, I get 2x plus y. Ooh, those are not equal, right? Does everyone see that? Okay. Does everyone get the warning? Right? You could try that procedure that I just taught you, and you would not be able to answer the question. And it's kind of fun. You should try it. If I had more time, I'd let you go get stuck in the middle of it, but we got to keep moving. And you should try it. So what's the rule? Don't go using that technique until you verify that the equation is exact. And that's such an easy trap to fall in. Okay. How's everyone doing with that? Yeah, Troy.
Didn't on the back page, did we find the partial in terms of x of the dy given?
So what we always do, once we've put it into differential form, is we take the partial of one of, now notice I have my x's and y's out of order here, so that might be the issue. But I take this was the differential y, so I'm going to take the partial derivative of it with respect to x. This was what was being multiplied to the differential x, so I took the partial of it with respect to y. And that's that check. I think we're okay in this case. Oh, that's good.
Okay.
Yep. Great. Okay, so folks, now let's do this trick. Okay. Let's go ahead and multiply both sides of this equation by x. When I do so, I get 3x squared y plus y squared x plus x cubed plus x squared y prime equals 0. Multiply the side on 0 by x, so I just still get 0. Now if I set this up into differential form, if I do my check now, if I call this m and I call this n, if I do my m sub y, and I do my n sub x, n sub x would give me 3x squared plus 2xy. Now, this ODE, now this is exact. Okay. Ooh, clever move, right? So what's your question? Yeah. What's that? I'm sorry? I can't hear you, Troy.
I could be wrong. This means that there's a needle in the stack, right?
Oh, I said now this is exact.
Oh. Oh, you fixed it. Okay.
So the ODE was not exact to begin with. So what did I say to do? In this case, I told you to multiply both sides by x, and now we've got an exact ODE. So what's your question? Why did that work? Why did multiply by x fix it? Okay? I'm not going to be able to get into that tonight, and I'm not going to hold you responsible for it, but this goes through the discussion of where that factor of x came from, and it's a way of sometimes being able to turn ODEs that aren't exact into exact form. Okay?
Are we able to do it with the other variable, like y?
It has to do with you take the partial derivatives and you divide by, and then you see whether you can divide out all of the y's, or in this case, if you write it this expression, if you're able to divide out all of the x's, if either of those cases work, then you can come up with a factor that you'll multiply to both sides. Okay? Yeah, so there's all sorts of I'm just pointing this out to you because I'm not going to test you on questions like 7, 8, and 9. Okay? But I'm just pointing out to you just how in-depth this field can go. We're just scratching the surface with a few topics. Okay? The idea though is there's two lessons here. The first lesson is don't just jump into a procedure unless you've checked all of the boxes that say you're allowed to start doing that procedure. And here it would have been very easy to get started with this and waste 15 minutes on it before you realize it's not exact, this method's not going to work. Okay? The next thing is that there are sometimes fixes, or there's sometimes these kind of clever methods that people have developed to turn one equation, one ODE, into another form, so then you can keep doing the technique that you learned on it. And that actually is a common thing that we'll be doing next week. Okay? For example, folks, what's the easiest type of ODEs you've learned how to solve? Separable. We're going to learn techniques to take non-separable ODEs and sometimes turn them into separable ODEs so we can then solve them. Okay? So that's just kind of a hint as to what's coming. And if I had more time, I'd work through this with you. Does everyone feel like they could solve this ODE? I'll give you a hint. A lot of times you can actually come up with that psi of xy on your own just through a process of trial and error. I want you to show me this procedure and learn this procedure. But you might be, let's see here. This was a partial derivative with respect to y of a function. This was a partial derivative with respect to x. Could you start reconstructing it? My technique of integrating partial differentiating is just a way to reconstruct it. But you might be able to reconstruct aspects of that, because it's all polynomials, on your own. But if you want to be sure, you follow the technique that I showed you. Okay. Folks, that's all I'm going to touch on exact ODEs, mainly because you had a lengthy pre-work in it. But if you still have questions, please feel free to come by and see me. In class, I have to rush through these topics. In office hours, well, I don't have a lot of students. I don't have to rush. Sometimes I still have to go quick. But I can give you more individual attention in office hours. Folks, I do recommend getting a 3-ring binder for this class to organize everything. If at the end of the semester all you have is a backpack full of papers, that's fine, but I don't know how helpful it'll be for going forward. So I do recommend getting some sort of 3-ring binder to organize everything.
I recommend something of this size. I had that originally, but you run out with this. Works out. Thank you very much.
Also, I tend to be one of those people that doesn't buy something that does not work.
Okay.
Yes.
There's two.
I'm short one. Is anyone using a tablet? Or is there an extra one floating around?
Wait, the class is not over.
No, we're going to keep going.
Okay. I was like,
Yeah.
wait, because it says in class.
You guys paid for an hour and 50 minutes, and by golly, I'm not going to shortchange you. All right. So, in honor of Joseph or Leonard Euler and Joseph Lagrange, not our Lagrange in here, but we've got a method for it's a fairly I think it's a fairly complicated way of solving first order linear ODEs and IVPs. Okay. Tomorrow next week we'll learn, actually for your pre-work for next class period, you'll learn a better way to do this. But this method is actually the one that we carry over into higher order ODEs. So I want to start exposing you to this method now while things aren't too messy. So when we do it for second and third order ODEs, it doesn't feel like you're learning something for the very first time. Okay. So this is I think I'm right that this is kind of a clunky way of solving first order ODEs, but it will be helpful for solving nth order linear ODEs. And it gives us a topic to explore. It gives us an opportunity to explore the topic of superposition, which is what we explored last night. Okay. By the way, in this section, I'll call it Euler-Lagrange method. Later on in the course, it'll be called the method of variation of parameters. They're basically interchangeable terms, except we like to use Euler-Lagrange for first order and variation of parameters for higher order. Okay, so let's go ahead and practice this, and I'm going to practice it without too much notation here because we're running out of time. So this is the ODE that we want to solve. And as math people, when you're asked to solve a question, our favorite thing to do is solve a different question instead. Okay? So we're going to solve, so first of all, let's classify it, because it just, sorry folks, I think when I printed it off, it doesn't say to classify it, so we're going to classify this. This is a first order linear non-homogeneous ODE. Okay. And I think the first thing I'm going to do actually is let's first put it into normal form. Put into, I don't have a good word for this. A different form. I don't know the word for this. So I'm going to divide both sides by t here. To make sure that I get a 1 for the coefficient function in front of y prime. And that's actually a very common first technique for solving ODEs, is to get rid of the coefficient function in front of your highest order derivative. Notice I didn't put this into normal form because I didn't take the y term over to the other side. Okay, does everyone see that? Okay. So the second step is to, it's kind of the smart aleck answer, solve a different problem. We're going to solve y prime minus 2 over t y is equal to 0. The corresponding what? So the original equation you can see here, folks, is first order. It's linear because look at y and y's derivatives. I'm not raising those to powers. I'm not taking the sine of y. So this is first order linear what? What is this? Because this isn't 0, what is this? Non-homogeneous. Remember that? It was a couple weeks old. This is the non-homogeneous equation, right? So what are we electing to solve instead? The first order homogeneous. Okay? Now in this case, we're really lucky because first order linear homogeneous equations will always be separable. Notice that the original, in fact, I was going to say this up here, when we were classifying it, note that it's not separable. The original ODE is not separable. Okay? But we're going to go ahead and solve the corresponding homogeneous ODE. So let's do that. This gives me dy dt as my independent variable is equal to 2 over ty. And so if I separate the variables, we get 1 over y dy is equal to 2 over t dt. Okay. Integrating both sides gives me the natural log of the absolute value of y. is equal to 2 natural log absolute value of x plus c. Did you ever think that integrating would be a step you don't even write in your math career? We just do it. Oh, yep. Oh, doggone it. What did I do, folks? I do that. I don't know. That's my favorite error to make, is to change the independent variable from x and t. Books, just so you know, will always use just x or always use just t, so they don't make that error. But I've tried to mix it up for you just to give you practice with both, and then I fall into my own traps. Okay. How are we doing, folks? What's that? Yeah. So then this is the old move where we get absolute value of y is equal to ce to the 2 natural log absolute value of t, or absolute value of y is equal to ce. I'm going to go a little bit slowly on this because we haven't done it as much in here. So I pulled that power of 2 in. So then I can say that absolute value of y is equal to c absolute value of t squared, or just y is equal to ct squared, with all those corresponding pluses and minuses being absorbed by the undetermined constant. Okay. Now, that's a solution to the what? Homogeneous equation. Okay. So the third step is to guess. Okay, this method is called a there's a fancy word for it. They call it an on-shots, which is like an educated guess. Okay? We're going to guess that our solution is going to be linearly independent from one of these solutions right here. So if I were to pick, for example, c is equal to 1, we'd have y equals t squared solves the homogeneous ODE. Okay? So our guess is that our solution to this will be y is equal to some function v of t times t squared. Okay? So what we're guessing is that our function will be we haven't figured out what that is yet, but we're going to suppose that it's kind of like we're riffing off of that t squared solution that we found. We're going to multiply it by some other function that we haven't yet determined. Okay? And then later on, we will continue with that. Okay? So I'll finish this out next time because we're not going to make it. I thought we could. What we do here, just so you know, is we differentiate both sides. Then we go plug our guess into the solution, and we will actually be able to solve for our guess when we go plug it in. Okay. So folks, I had some great questions about what was going to be due when. So just as a reminder, you've got pre-works due next time. 2 pre-works. Yeah. They're short though. Is that true? One's just a front and back. One's just a front and back, and the other one's 3 pages. So they're short. So just as a reminder, folks, next time we meet is February 1st. So you've got these 2 pre-works that I'm handing out now. They're due tomorrow night. These will always be due 1 day prior to this. You're welcome to get started. You're welcome to get started on the homework sets. You'll see that although you have 3 of them, some of them are only 1 page. Let's see what this one is. Oh, that one's 2 pages. So some of these are, one of these is only 1 page. So how about that for your homeworks?
So what is the use of matrices in like engineering? What's an application of that?
Finite element analysis.
I both of those things not fully understanding, but okay.
Well, have you ever wanted to know multiple unknowns, the solutions to multiple unknowns?
Yeah.
Like, you're trying to figure out the time, the weight, and the temperature of your object. You've got 3 unknowns. Now, if those are linear equations, then you can use this row reduction method for solving them.
Okay. So then how does the cross product play? Is that a type of linear, or is that not? Because I thought that's where you can... Or is the cross product not...
Cross product is something we do with 2 vectors that live in R3.
Oh, okay.
So one, we won't study it in linear algebra because all of our results we want to apply to any number of dimensions. And cross product is only something we can do in 3 dimensions. So we won't study that here.
So we can do 4th dimensional math.
Well, that's what you did. Whenever you solve a system with 4 unknowns, you're doing 4-dimensional math.
Thanks, Charles.
Yeah. Hey, we'll see you, Christian.
See ya.
See you, Norman. Gustavo.
See ya.
Take care, Phil. Phil, are you doing okay with the pre-works?
Kinda. I usually get home from work at like 11 p.m.
Okay.
So it's like sometimes I can't get them done.
Okay.
by then.
So what you could start doing is, if it works for you, I don't know, but you can always do these ahead of time, like on the
Yeah,
weekend.
I think I'm gonna start doing it tonight.
Good, good.
'Cause, yeah, I work. I get home tomorrow.
You got a
at
busy
11.
schedule, yeah. Yeah, take care. Vitaly, did you have a question for me? Nonlinear functions.
Yeah.
Not really. So what we could do is, let's say I gave you something like sine of t x plus 3t squared y plus the natural log of t z is equal to 3. So this is not linear in terms of the function t, but it is in terms of these functions.
What's that?
Take care, folks. And so if I gave you a system of like 2 more of these with x, y's, and z's, then you could construct a matrix that has nonlinear components in it. But it's important to realize we're not solving for nonlinear expression. We're solving for these linear terms x, y, and z. Now, to row reduce this would require a pretty good knowledge of inverses, and you'd probably have to restrict yourself to where these functions were 1-to-1 to be able to use inverse functions. So like, for example, if I want to get a 1 here, I would divide everything by sine of t. But then multiply, I mean, it gets very, very messy. But we will actually do some work where we put functions inside of here, and the function that we solve for might end up being nonlinear, but we will do linear techniques on it. But it would not work for nonlinear, like if this, the variables have to be linear variables, if that makes sense.
I was just asking because there are circuits that I deal with that are sometimes non-linear because the resistance changes.
Yeah.
That's why I was wondering
Yeah.
if I can use Kirchhoff's law for non-linear.
So I'm not familiar with circuit analysis, but there are techniques for looking at nonlinear systems of equations and saying, let's go look at where those nonlinear systems might be close enough to linear where we can do a linear analysis on them. And then we'll touch on that at the very end, but we probably won't go into that much. Yeah. Cool. Great question. Hey Connor, how's it going? Did you get a chance to think about the course? I think you should have a little, maybe 1 more week. Is it tomorrow? Oh, I don't know. Okay, I didn't realize that.
I think it's tomorrow, but I was looking at it and I should probably double check.
Okay. Yeah, I don't recall that. If you choose to audit it, great, but I think that all has to be done at kind of the same time. Or, but if you just decide, like, you know what? I'm saying
It takes me 2 minutes to do that.
No worries. So I don't want to push you into saying that.
That's just like how they look for new ones.
I will say that the workload at the start of this class is heavier than the workload in the second half. That doesn't mean like it's easier, but the workload is less, if that makes sense. Cool.
I know I can look, but I can't remember if you had
Yeah, I do. I have office hours tomorrow from 3:30 to 4:30. Yeah.
I'll be able to, maybe might be able to drop by.
Okay. I'm pretty much around after, let's say I've got classes in the morning and then I've got a meeting at noon. And it's pretty much around my office after 1 p.m. until
A night?
5:30 p.m. There's time in there, you can just swing by if that works. Yeah.
But the waiters have it on the city customers who might be able to.
Okay.
And then just drop.
Well, if you decide that it makes most sense to drop and you're not able to see, just shoot me an email, just let me know. I completely understand.
I really appreciate that.
Yeah.
Yeah, no, I should. I have like, because when I put it on, I know I had that kind of week to look at it, but I've been needing to look at it this week as well.
No worries. Okay. We'll keep them posted.
I appreciate it.
And maybe I'll see you tomorrow.
Have a good night.
Good night. Yeah, let me see. Bridger and Josiah, how we doing?
I had a question.
Yeah, shoot.
So this one, like, you ended up doing X5 like T1.
Mm-hmm.
Steve, like, I get that
Mhm.
you would use it as a T, but isn't it also like T would just be 0? So you could just completely not write that whole thing?
So if I had my way, I could go back and fix this equation and put a non-zero variable in it. Like I'll put a 1 near the first two rows or some number. I think Josiah asked that question and I was flipping on answering it. I'm trying to imagine a scenario where you would have started with truly having 5 variables show up in an equation and writing them. And so I think that this still works. It's just that we don't usually encounter it all that often. But I could say let's say we have these 3 planes. 3y plus 2z equals 4, and 5y minus z equals 3, and y plus z equals 2. If I choose to think of these as living in R2, then it's just, I've got the variables x and y and z. But if I tell you that they're living in R3 here, x, y, and z, these are planes that are that all have 0 for their x component.
Okay.
Right?
So then they'd just be in the ZY plane?
So they all have so they'd all be in the ZY plane, and so they'd be like 3 lines. Well,
But then couldn't you then bring it back down to
I need to think on that. I really wish I could. I need to go back and fix that problem. I don't really want to get into that discussion.
No.
So send me an email on that, and I'll give you both a point. Remind me there was the 2 of you.
Okay.
I'll give you both a point for that, and I need to go back and change that. I want to put a 1 in there because it's not. I can't think of a scenario where this would have happened. So let's just go back and put that in. Yeah. Great question.
Okay, thanks.
Catherine, how's it going?
Do we meet
Yeah.
here?
Oh,
I'm glad
that's right. I forgot we're also doing the
Yeah.
going through the accommodations. I remembered that we were going to look at the most recent homework set. But yeah, let's go do that. I'll just leave this here for right now.
Okay.
Let me shut it off.
You, Charles.
Thank you.
Yeah, take care, folks.